All right, so this video is going to be on some aromatic compounds, and I think they're all kind of fancy, but these ones are extra fancy because they got some weird shapes, they got some charges, and they even have some triple bonds in them. So let's take a look. So really, what we want to do is watch me struggle draw this one because it's like kind of ridiculous. It's kind of hard to draw, but I'm letting you watch just so you can appreciate the end product, or you can just appreciate how difficult it is, even for me. I've been doing this forever. But, ooh, that don't look too bad. That's pretty good. All right. So, um, there we go. Alternating pi bonds. And really, what we want to do is try and determine if these guys are aromatic. You guys excited yet? I'm excited. Woo! Ain't nothing wrong with little minions. Despicable me. All right, so this thing has 14 pi electrons, and it is called a 14 aniline. Okay, so the guy on the right, he's got 18 pi electrons, and it is called 18 aniline. Okay, so are they aromatic? Would be the question. So again, you really have to just know, or you'll probably be told that they're planar. Okay, so I'm telling you, it's planar. And then they're clearly cyclic. They are conjugated, and they do meet the 4n plus 2 electron count. Okay, so the Huckel's rule is satisfied. So they are aromatic. Okay, so let's take a look at a few more. So this guy right here, that's 10 aniline. Okay, so we got 2, 4, 6, 8, 10 electrons in our pi electrons, right? So it is cyclic. The question is, what about the other stuff, though? I'm not telling you it's planar because it's not planar, but let me show you why. So if those hydrogens, if they were going to be in there at the bond angle that they are supposed to be, they would just be bouncing up on one another. So the steric hindrance requires that the ring puckers, and it is not planar. So let's see my sad attempt at drawing this. Shouldn't be too bad. Oh, I'm about to cross these guys because that's what happens. So it does ring pucker. All right, let me fix something real quick. Boom, boom. All right. Maybe you can see it. Maybe you can't. The point is that the two center carbons, right where those hydrogens are, they're actually one's pushed up and one's pushed down, and that ring puckering for basically eliminates the planarity of this compound. So it's not planar, and therefore it is not aromatic, or it is non-aromatic. Okay. All right. So what if we had a 16 aniline, a 20 aniline, or a 22 aniline? Okay, and all of them were planar. Okay, are they aromatic? So let's take a look at the electron count. So 16, it goes to the 4n rule where n equals 4. 20 would be when n equals 5, and then 22 is when it does work for the 4n plus 2 where n equals 5. So so that is aromatic, while the others are not. They would be anti-aromatic, assuming all is conjugated, cyclic, planar, which they are. So they are anti-aromatic. Okay. All right, so let's take a look at a couple more. So this one's pretty cool because it's like fused benzene rings. And we know benzene is aromatic, right? So what happens if you jam them together? This is naphthalene. It's kind of gives that scent that you smell if you've ever heard of mothballs. It's the same. That's the stuff. This one right here with 3 benzene rings fused together is called anthracene. And I said benzene rings. I mean, obviously, like some of them, the 2 on the right don't look like it, but you get what I mean, right? They're 6-membered rings jammed together. We got 10 and 14 pi electrons for each of them. They are planar, they are conjugated, and they are cyclic. So 4n plus 2 is satisfied, and they are aromatic. Okay, so that's really all we have to do. But let's take a look at some aromatic heterocycles, because these ones they're more fun, I think, because you can ask a lot more questions about them. But heterocycle is something that contains atoms other than carbon. So it's usually going to be like oxygen or nitrogen, but you could have like phosphorus or sulfur or something like that. So you got the pyridine on the left and then the pyrol on the right. Okay, so notice the subtle difference between the two. The nitrogen on the right has three sigma bonds and a lone pair, while the nitrogen on the left has two sigma bonds, a lone pair, and a pi bond, right? So they are both planar. And are they conjugated would be a question. 4n plus 2 pi electrons? I don't know. And they're definitely cyclic, okay? So we got two of those criteria met to determine if they're aromatic. So let's take a look at the conjugation. So clearly on the left, it's like benzene, right? We got those electrons shifting around. If we use the lone pair on the nitrogen and pyrol, we can do the same thing, okay? The question would be the lone pair on the left. Can we use that to do resonance as well, right? So let me redraw this guy, okay? So this nitrogen right here, what's the hybridization would be the question, right? So it's a nitrogen with 3 regions of electron density, and so it's sp2 hybridized. So that means it's got 3 sp2 orbitals and 1 p orbital, okay? And remember that p orbital is used to make pi bonds, right? So the 3 sp2 orbitals are what make the 3 sigma bond, or they can make up to 3 sigma bonds, and then the p orbital is used for the 1 pi bond that nitrogen has, right? Sorry, let me write this. At most 3 sigma bonds, okay? So if we have 2 sigma bonds already taken care of, we have 1 pi bond already taken care of in blue, then where does that lone pair on the pyridine reside? Well, that must reside in an sp2 hybridized orbital, because the p orbital is already occupied, and we had three sp2 orbitals that could be occupied by electrons. Okay, so since that p orbital is already occupied, then the sp2 or the orbital containing the lone pair cannot participate in forming a pi bond. Okay, so it's essentially going to look more or less like this. Let me draw it red, and then I'll draw my p orbital poking up and down. Okay, the lone pair would be like in that one. And so the point of me drawing it like this is to show you that it's actually planar and it's sticking to the left while the other sigma bonds are to the right, and then the p orbital is up and down, and so that's going to actually be parallel with all the other p orbitals, while the lone pair is in an sp2 hybridized orbital that's perpendicular to those orbitals and therefore cannot participate in delocalization of those electrons. Okay, so that means it has 6 pi electrons, and therefore it is also conjugated, it's planar, it's cyclic, and so it's aromatic. Okay, so let's take a look at Pyrol. So we already said that the lone pair can do resonance because we used that, and it's there, right? So it's adjacent to a p orbital, so why not? Okay, it is cyclic, it is planar, okay, and so there's the 2 pi electrons, 2 sets, right? And then that nitrogen, is it sp2 hybridized or is it sp3 hybridized would be the question, right? But since I told you we can use those pi electrons to do form a resonance structure, that resonance structure would look like this, where this nitrogen has a positive charge and the negative charge is on the other carbon, right? So that means in this particular resonance form, that is an sp2 hybridized nitrogen. Once an sp2, always an sp2, okay? So what that means is that the lone pair above actually resides in a p orbital. Otherwise, it wouldn't necessarily be able to participate in that resonance structure or the delocalization of the electrons, okay? And so that's why that nitrogen lone pair does reside in a p orbital. Okay. Remember, resonance structures are just you take the average of all of the resonance structures to give you what the real molecule looks like. Okay, so what we've got is 6 pi electrons. It's conjugated, it's cyclic, and it's planar. So therefore, it is aromatic. And notice the difference between the two, right? I already told you that the Pyrol has the lone pair and 3 bonds to that nitrogen, while the other one had a lone pair but 2 sigma bonds and 1 pi bond. Okay. Now let's take a look at histamine, because it's got a similar thing going on, right? So we have a heterocycle, and we've got 2 different types of nitrogens in there, right? So this nitrogen right here, it's got a lone pair that can participate in resonance, and so kind of just like the Pyrol, right? We've got a lone pair that resides in a p orbital. Okay. And this lone pair over here is an sp2 or is in an sp2 orbital, because that nitrogen is sp2 hybridized and this already has a pi bond. So that p orbital is occupied, and therefore that lone pair must reside in an sp2 hybridized orbital. The other lone pair resides in an sp3 orbital, and it can't change because there's nowhere it can participate in resonance. Okay. And so these are the types of questions we need to be able to answer. Where is that lone pair? What orbital does it reside in? Okay. And so we can take a look at other heterocycles as well. Same thing. This is furan. So let's just kind of draw these p orbitals up and down. There's 2 lone pairs there, right, on that oxygen. Well, yeah, you can use one for resonance. We do that all the time. Okay. So that means that one of these guys is in a p orbital, okay? And what does that mean for the other one? Well, the other must be in an sp2 hybridized orbital, okay? And that's because you can make a resonance structure. Either you can go to the left or to the right, but it doesn't matter. It still has to be the electrons in that vertical p orbital that's parallel with the adjacent p orbitals, okay? So that is also aromatic, once you count everything up and identify whether or not it's planar. And it is, because I'm telling you. All right, so this fancy thing right here, we've got 2 p orbitals here and 2 in here. Now, similar thing with the lone pairs in the oxygens, right? So we can definitely use them to create a resonance structure. Okay, we can do that on the top or the bottom, but it's not conjugated completely. Okay, so we can definitely create the resonance structure, but once you do it, it has to stop at the carbon, and that carbon, the electrons have to reside on the carbon, because they can't create another bond to oxygen, because that p orbital that's there is occupied by a lone pair. There's 2 guys there, and they don't have anywhere to go. Okay, so there's nowhere for them to go. If they went to the left, then you'd have way too many. You'd have 4 bonds and a lone pair to oxygen, and that's 10 electrons in its valence shell, and we can't have 10, right? So it's non-aromatic because it's not conjugated completely. So let's take a look at this fancy heterocycle. We got 2 nitrogens in there. What you trying to do with 2 nitrogens? Well, not trying to confuse you, because you just apply the same logic, right? Those 2 nitrogens, if you look at them as individuals, they're just like the pyridine, right? So they're both in sp2 hybridized orbitals. The lone pairs are in sp2 hybridized orbitals, and so therefore it is aromatic because we have 6 pi electrons. And that's it. So super chill. These guys are easy to do. This next section, though, is pretty fun as well. So I like to mess around with these. I don't know why. It's just kind of like, oh, dang, I can answer that question. That makes me feel good. So it's kind of tying together acidity and stability. So charged aromatic compounds, right? So let's say we have this cyclopentadienyl, and it's not conjugated, right? Well, that means it's non-aromatic, okay? Because it's a sp3 hybridized carbon, sp3 hybridized carbon right there. But if we hit it with the base, remove the hydrogen, that gives us 2 electrons at that site, and is a negative charge. And those 2 electrons now can participate in resonance. And what do you know? It can go around and around and around. You can shuffle that a negative charge to each and every one of those carbons. So you have 5 different resonance structures, and therefore you have 6 pi electrons. It's planar, it's cyclic, and it's conjugated. So it is in fact aromatic now. It went from non-aromatic, hit it with a base, it became aromatic, okay? And this compound is called a cyclopentadienyl anion, okay? Now, what we want to do is compare this to other very similar structures, okay? So, let me draw them out real quick. I'm going to cheat. I'm going to draw a nice ring, and then I'm going to copy and paste that for you. Bloom, bloom. Okay, so the first one, we have the cyclopentadienyl anion. The next one, we got a positive charge, and then the next one we have a radical. Okay, we still have those pi electron, or the 2 double bonds, right? So just real quick, I'll rewrite the names for you. Cyclopentadienyl anion. I'll copy and paste this. Cyclopentadienyl cation, cyclopentadienyl radical. Okay, not too crazy, pretty chill. So we already established 6 pi electrons on this guy. It is aromatic. Okay. Now for the middle compound, I highlighted the pi electrons in blue. There's 4 of them. Okay. Now, is it conjugated? Would be a question. Okay. So why do we care if it's conjugated? Which it is, because you can have that pi electron go to the occupy that vacant p orbital and just shift the positive charge somewhere else. So since it is conjugated and it has 4 pi electrons, that means it's anti-aromatic. Okay, if it wasn't conjugated, then it would just be non-aromatic. So this one right here, yeah, those, you can do resonance structures with radicals. It's got 5 pi electrons though, and so it's non-aromatic. Okay, doesn't have 4 or any variation of 4n plus 2, so it's non-aromatic. Remember, the aromatic compounds are very stable, while the anti-aromatic are very, very unstable. Okay, and non-aromatic, that's nothing to write home about. Those are just whatever, right? Typical reactivity, nothing fancy. Okay, the other 2 are anomalously like drastic in either direction. Okay, so that hydrogen I highlighted in blue, that pKa is 15. 15? Are you serious? That's crazy. Remember that time when water was higher than that? So that's how acidic it is. That's how stable this compound becomes. Okay, and just for reference, like, I don't know, ethane's like 50. So that's like another carbon hydrogen bond. That's like insanely like hard to remove. And so again, aromaticity, stability. Okay, and that's the most stable CH or most acidic CH bond we've seen so far. We'll see some other ones that are a little bit more acidic, but we'll see those later. Okay. Let's see here. But yeah, that's crazy, right? It's more acidic than water. Are you serious right now? All right, so this guy right here, that has a pKa of 39. Like, why is it 39 and why isn't it 15 like the cyclopentadienyl or cyclopentadiene, right? So let's say we remove that, and then what we end up with is this guy right here. Okay, so that's hella conjugated. So what's the problem here, right? It is planar, it is conjugated, it is cyclic. So what's the problem, right? Why is this pK so high? It's almost like a regular benzene, right? So benzene's benzene's 41, super hard to mess with. It has 8 pi electrons, so it's anti-aromatic. Remember, anti-aromatic means it's very unstable. And so remember, when it comes to acidity, the more stable the conjugate base, the lower the pKa. So since it's got an unstable conjugate base, it's a high pKa, so 39. All right, so let's talk about cations now. So we did see a cation that was anti-aromatic, but let's see if we can find one that is aromatic. So this is called a tropylium cation. It's basically a 7-membered ring with a positive charge, as well as 3 pi bonds, right? So it is planar, it is cyclic, and the question it would be, it's got 6 pi electrons for sure. Is it conjugated? Yeah, maybe. Yeah, you can shuffle those pi bonds around and move the positive charge somewhere else. It's easier if I show you the flow of electrons that go in the counterclockwise, right? So boom, those electrons reside in the vacant p orbital now, and then it just shifts the positive charge everywhere. So it is conjugated, and therefore it is aromatic. Okay? And so that just kind of shows you that depending on the size of the ring, it could be positive, it could be negative. You have to make sure that you follow all the criteria and make sure that it meets it. So in order to determine if something is aromatic, non-aromatic, or anti-aromatic, okay, you can't just say like, oh, it's got a positive charge, so it's anti-aromatic, right? So you have to count. You got to make sure it's cyclic, conjugated, and planar. So assuming the rings are planar, label each of them as aromatic, anti-aromatic, or non-aromatic. Okay, so let me draw these for you real quick. All right, so this next one is the worst. I'm about to struggle. Watch. Here, let's just make this happen faster so that it's boom. That is absolute garbage. That looks so bad. All right, let's redo this. Okay. We got one step at a time. Ugh, it's so not good. I'm gonna run with it though. So, yes, I'm even gonna copy and paste that one because that's worthy of reproducing, even as bad as it may be. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. Okay, that's what they got. We got a positive charge on the one on the left and a negative charge on the one on the right. So it's got a lone pair. Okay, so let's look at this propene, cyclopropylium. It is aromatic because it's got 2 electrons, right? That's when n equals 0. What about this one right here? It's got 4 electrons. It is conjugated. It is planar. It is cyclic. But since it has those 4 pi electrons, remember that follows the 4n pi electron rule and is therefore anti-aromatic. All right, so 2, 4, 6, 8 with the vacant p orbital. Definitely conjugated, right? Bada bing, bada boom. So what is it, right? Since it's got 8 pi electrons, that means it follows the 4n pi electron rule where n equals 2, and it's anti-aromatic. Okay, so let's take a look at the next one. 2, 4, 6, 8, 10. It is definitely conjugated. Let's highlight those for you. 10 pi electrons, conjugated, planar, cyclic. So it's aromatic. Now, I kind of just thinking about the trend, if you will. So we've got 5 and 9. They were both negative and they were both aromatic. But then we had a 3-membered ring that was negative and not aromatic. It was anti-aromatic. But the 5 and the 9 actually had even numbers of pi bonds. So maybe there's a trend there. Maybe you can look into that more. I'm not going to. I don't care. But maybe if you want to try and find a shortcut, maybe that's something to look into. Let's draw something else that's fancy, okay? Okay, so yeah, this one's crazy. So the reason why I really want to do this one because it's got triple bonds in it, and it's so Gen Chem right now. We're about to Gen Chem so hard right now. Because you need to remember that stuff to some degree, right? We're not doing Gen Chem every day, but I'm gonna extend that bond like real long, and you're gonna be okay with it. I'm sorry. So let's see. 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, so we got everything taken care of. Is this aromatic is the question. Okay, so it does have a proton NMR resonance at 7.6 ppm. So since that is highly deshielded, then that does indicate aromaticity. Okay, because it's like anomalously deshielded, right? It's in the aromatic region. And it likely corresponds to those alkene proton resonances. Now I'm thinking that this is like highly symmetrical, but whatever, it's just drawn terribly. But it doesn't matter. The point is we want to see if it's aromatic. So let's take a look at these alkynes, right? So we've got 2 pi bonds in each of these alkynes, right? They are those 2 carbons are sp hybridized. So what does that mean in terms of orbitals, right? So that means we have to have 2 sp orbitals as well as 2 p orbitals, and that's for each carbon in that alkyne, right? So what's that going to look like? So let me remind you, this is where we gen chem. So let's say I'm going to do these each in red now. Usually I do red and blue, but the vertical p orbital is in red and the horizontal p orbital is in blue. Okay, so this is just to show you. Remember, we have a px, py, and pz, and so these are 2 of those p orbitals projected into the x, y, or z plane, and so those red p orbitals are vertical, and the blue p orbitals are going to be horizontal. Okay, so what's the significance of this? So let me just, I guess I want to imply, like, or write, they're into the screen. The blue p orbitals, they're into the screen as well as out of the screen. Okay, so just to give you an idea as to what we're looking at. So why is that significant? So let's say we draw out our p orbitals, right? The red ones, of course, because those are up and down. And remember, in order to have something be conjugated, you have to have those p orbitals be parallel with one another, so that way they can line up in order to form that pi bond, right? That new pi bond that would form after delocalization of the electrons. Okay, so everything seems to line up, right? We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 of them just all in a row. Okay, so 18 p orbitals all in a row. And so since they're all in line and they're parallel with one another, right, or they're all like adjacent to one another and they're parallel, then that's we're in line for establishing aromaticity, right? So these blue ones are, since they are horizontal, they're not they're perpendicular to the red ones, so the blues can't form pi bonds with the red ones. Okay, they are therefore not involved in conjugation. Okay, so what's the significance of that? Again, that means that 2 of those pi electrons in each of the alkyne, 2 of them don't participate in the delocalization of electrons. Okay, so that means that we have 18 total pi electrons, and that follows the 4n plus 2 where n equals 4, and that means that it is in fact aromatic. Okay, so don't forget the alkyne orbitals. So only 2 of those 4 pi electrons can participate in delocalization of electrons. Okay, and don't get too confused. This is a great question. It's a tough one, but it's also really easy if you've done your work. Okay, so get that practice in. Okay, bye.